Good morning, hello, good afternoon, good evening, if you're watching this on catch-up. Hello, it's IGCSE physics time. We're skidding towards the end, you know. We've got a lesson next week, and then I'm going to do a sort of recap, kind of past paper questions, quiz type lesson, because waves has been big. But yeah, we've only got 2 lessons left after this one. So we're finishing off waves, and then we'll have done 3 modules out of the 8 modules. Right, so yeah, we're going to do all the waves practicals. So if we were doing IGCSE in the classroom, then you would do, this would be like an examined bit. So there'd be various practicals that you did, and I would like walk around the classroom and you would be doing your practical and you'd be writing down your table of results. And then I'd mark the results and it'd go towards your exam grade. At IGCSE, you can choose not to do that, but you still need to know how the practicals work, and then you just write an exam paper about how the practicals work. So we will look at how the practicals work. Okay, we'll start with the ripple tank, because I have showed you this, and then I said we'd come back to it, so let's go back to it. Here we are. So it's basically like a tray of water, and it's got a light bulb above it. And you've got this oscillating paddle in the tray, which has got, you can see like there's a motor here, which is connected to the electrical mains. And it's weighted on one side. So the motor spins around and basically it just makes the paddle go up and down. Yeah, that's what oscillating means. So the paddle goes up and down and it makes these waves in a little wave tank. It's probably about 5 centimeters deep. And then underneath, you've got this little viewing screen or piece of paper, which the light shines through the water and you can see the waves on the screen. And yeah, it's plugged into a power supply. So my first question is, what are some dangers to look out for? It's not rocket science, this bit, is it? What are some of the dangers of having a motor which is attached to an electrical power supply in some water? Electrical shock, right? Just be careful about water and electricity. Water and electricity not mixing so well, so be careful that you don't get the water near the electricity. Okay, let's make, I've been saying that it's a terrible model. It's actually not awful model of a ripple tank. So I said to bring some sort of clear tray, like Tupperware or maybe glass baking dish. What I want you to do first of all, I couldn't work out a way of shining a light through it and being able to see the waves on the ground. You can have a little play after this if you want to, but shining a torch onto the water as we pour it into this tub, I think is going to help us to see the waves better. So the first thing I'll do, well, yeah, let's pour some water into the tub, shining a torch on it, and see if we see any waves, first of all. This is where it gets a bit tricky because I'm holding the camera. I'm just going to have to stick this in my mouth, but it'll be fine. Okay, so get your tub. Maybe just put your tub on an angle and shine torch into the tub and pour some water, okay? Right? Can I see waves? Oh yeah, I see waves. Okay, that's definitely waves here. Oh yeah. Very wavy. Right, so we're seeing waves. It's not a terrible model already. If I hold it to the side, what you can do is just just give it a slide, like slide it in one direction, and then watch what happens. Slide it in one direction, and then watch what happens. What is happening? So you can use wave tanks. Wave tanks, they're really just used for kind of educational purposes. You can use them to demonstrate reflection and refraction and diffraction. So what am I demonstrating here? What is happening here? What is this wave doing? Is it reflection, refraction, or diffraction? 5 seconds. It's reflection, right? So if we were stood around the tank, we might put different objects into the ripple tank and then we would watch the waves reflect. But this wave is just reflecting off the side of the tub, yeah? Okay. Let's model diffraction. This is where people on Facebook were getting really freaked out by wet blue tack. So if you do not like wet blue tack, this is not the activity for you. So I'm going to use my bigger glass tray this time, put it on a white background. I'm going to get a blob of blue tack. And yeah, I was getting very excited by this on Facebook. This was working really well. So first of all, I'm going to use quite a big blob of blue tack. We're going to look at diffraction. You remember diffraction? About how Light waves don't really diffract when they come through a doorway because the wavelength of the light is very small and the gap is very big, whereas sound waves, they're about the same size as the door, so the sound waves do diffract. It's when waves come through a gap or go past an object and then spread out, yeah? And the wavelength of the wave has got to be similar to the gap, or the gap's got to be smaller. So first of all, I'm just going to pour more water into my glass Tupperware this time, and I've got a big blob of blue tack. Are we going to see diffraction? What do you reckon? Right, camera going down, torch going in. And oh yeah, look at that! Oh, that is good, isn't it? Hey, oh, okay, so. Oh, I can't say, I'm loving this. I think this is very good, and now it's the favourite thing I've ever done. So did you see how the water wasn't spreading out around to the bottom of the blue tack, was it? Now I'm going to use a much smaller piece of blue tack. What are we expecting to see? More spreading? Less spreading? I totally told you. We're expecting to see more spreading, aren't we? Okay, so sticking the wet blue tack to the... Yeah, this is where it went wrong yesterday. It went wrong yesterday and I had to spend ages fixing it, and I've made absolutely no provision this lesson for making it easier. Oh, okay, so I'm pouring the water back. I hope you're doing this with me. If you've got some kind of Tupperware dish or recycling... Right, I'm just going to dry this dish. Sorry. There we go. In a second, after we've looked at diffraction, I'm going to ask you how we could use this ripple tank to model refraction, which is a really difficult question. What could we add to this ripple tank? How could we modify our ripple tank so that we can look at diffraction? So diffraction is when a wave changes direction, yeah, because it's changed speed. Right, so I've got a very small blob of blue tack here. Camera flipped. Torch in house. Okay, right. Oh my goodness, that's so cool. This is spreading out a lot more. Oh, it's so beautiful. Wow, I could watch this all day. Oh. Okay, alright. Sorry, boring telly. I could watch that all day. I just think that is totally gorgeous. So if you want to have a little play around after this, if you've got the stuff, try putting blue tack on both sides or whatever, and seeing if you can get it diffracting through a gap. If you've got a phone, then you could try and film it in slow motion and see what happens. But okay, last question then. That's the end of the practical. Oh, so no, I'll talk about that later. How would you use your ripple tank for modelling refraction? So if I asked you to get a glass of water and a pen, right, and say, can you show me refraction happening? I'm sure you would do that very easily, because we've talked a lot about how when light hits water or glass, it slows down. So if it hits it at an angle, you can imagine like a pen is the wavefront, and if like this bit of the pen slows down but this bit of the pen is still going fast, then the pen would turn, and this is what happens to light. A light wave hits something, it slows down, so it bends, right? That's what refraction is. And it usually happens, we're used to talking about it happening when something changes from one medium into another, right? One medium, like when it goes from air into water, or from water into, I don't know, glass or whatever. But we've just got water, so if you've just got a water wave, a wave which is made of water particles, let's say it's just in this tub like this, let's make it really simple. We've got a wave going to and fro. What can we do to make that wave refract? This is really hard. A couple of people got it on Facebook. Some people just got bored and started rickrolling me because I wasn't telling them the answer. How would we make that wave refract? You have to add something. Well, I mean, I suppose there are various things you could... Yeah, no, you'd have to add something, as far as I can tell. We talked about tsunamis last week. Do you remember? We talked about tsunamis and what happens when they're going through deep water and what happens when they get to shallow water. I've totally told you. The depth. We could change the depth. So remember we were looking at how mirages happen because light travels at different speeds through hot air and cold air. So light travel, waves travel at different speeds through shallow water and deep water. So a tsunami is traveling really fast in really deep water, and then when it gets to the shore, because the water is shallower, it slows down. It gets much higher, but it slows right down. So you could, it cut like a piece of plastic. You could try this at home and put it in to make the water slightly shallower on one side. And if you put it at an angle, you might see some refraction. I don't know. I couldn't be bothered to do that, frankly. Okay, what is this ripple tank actually for, though? So we actually need a new equation, our final equation of waves. Don't worry, it's very simple. Wave tanks are often used for modelling this equation, showing people how it works. Wave speed equals frequency times wavelength. That's not new for you, right? We learned that last week. So V, speed of a wave, equals F, frequency of a wave, times this cute little lambda symbol here, which means wavelength. But there's a new equation in town. The frequency of a wave equals 1 divided by the period of a wave. I'm assuming you're all right with this language now, right? So the frequency is measured in hertz, that's per second, how many waves per second, yeah? And the period is just measured in seconds. It's how long it takes one wave to pass a point, okay? Like one wave, just how long it takes, how many seconds. So just very quickly then, you shouldn't need a calculator for this really. Just have a little practice. Hopefully you can rearrange this, yeah? So frequency equals 1 divided by the period. So a wave's period equals 1 divided by the frequency. I hope you can do that. Oh, people have started liking this video who are watching live. That's great. You love new equations. So the frequency of a wave is 2 hertz. What is its period? The frequency of a wave is 2 hertz. What is its period? The period of a wave is 4 seconds. What is its frequency? One wave passes a fence in a harbour every second. What is the period of the waves? Have you done that? Let's do the first one then. The frequency of a wave is 2 hertz. What is its period? Well, the period is 1 divided by the frequency. So it's just 1 divided by 2, which is 0.5, and it's seconds because it's the period. The period of a wave is 4 seconds. What is its frequency? Well, frequency is 1 divided by the period. The period is 4 seconds, so it's a quarter. Or if you change that, it's 0.25, and it's hertz because it's frequency. One wave passes a fence in a harbour every second. What is the period of the waves? Well, you had to spot that this was describing a frequency. So 1 wave per second. So the frequency is 1. So the period is 1 divided by 1, which is 1. Except that answer's not right. Why is that answer not right? You should all know this by now. Obviously, you all know that. Why is that wrong? The period is 1. It's wrong because I forgot the unit, but also I haven't put the unit on, so well done if you spotted that. So yeah, it's quite important that you find this really. I need to start finding ways to give you the PDFs that aren't on Facebook in case you're not on Facebook. But in my Facebook group, I've got this PDF of all the homeworks and reading that I think you should be able to do or practice after this lesson. And I've linked to a few like official Edexcel videos where they show you how you can use a ripple tank to measure the speed of the waves. So one thing you could do is you could put a ruler next to the ripple tank. Obviously, if you filled it with water, then it's quite helpful to have a mobile phone that films in that films in slow motion. Because what you could do is you could just take a picture of this, couldn't you, right? And then you could use the hashtag ruler on the side to measure the length of the waves. Obviously, I'm going really quickly here, aren't I? You'd generally make waves that were longer wavelength, so it's easier to measure. And you could also get a timer. This is what the lady does on the video. She's got a timer and she films the waves and then films the timer so that in slow motion you can see how many waves have passed a point in 1 second. And that is how then you've got the wavelength and the... So then you've got the wavelength and the frequency, so you work out the speed of the wave. I was watching my favourite online physics teacher, Lewis, who's in charge of the YouTube channel Physics Online, who I actually have met in real life when I was training. He was the head of physics at the school I was training at. It's just a total coincidence. And I wish we'd done this, but I didn't put this in the lesson because I only found it last night. He's got a big tray and he makes a wave like that. And then he says, another way of finding the speed of this wave. Can you think of it? You think of another equation for speed? How you would find the speed of that wave? It's better if the tray is longer. He just said, like, just measure the length of your tank. Measure the length of the tank and times it by 2. And then just time how long it takes the wave to go there and back again. And then you've got a distance and you've got a time. So you can work out speed. Well done, Lewis. Right, let's move on. Oh, okay, yeah, no, I'll ask you this. Here we go. So a student wants to find the period of the waves, the period, how long it takes a wave to pass by a point per second. So they put a mark on the side of the tank and they start a timer when the crest of a wave passes it, and then they stop the timer when the next crest passes it, okay? So they've got a mark on the tank, they start the timer when one crest goes by, and then they stop the timer when the next crest goes by. So you're measuring from peak to peak of the wave, right? So that's one wave. But there's a problem with that. That's not going to give a very accurate result. How can you improve that? It's a good start, but it's not everything you're going to have to do, really, to get the period of a wave. What are they going to have to do after that before they start calculating their period? Have you got it? Repeat! They're going to have to repeat. I've got a brilliant analogy for you to explain why it's important to repeat your results. Are you ready? I'm super proud of it. Imagine that you're standing facing a white screen. This is you. Sorry. You're standing facing like quite a big white wall. You're a safe distance away, and you know that on the other side of that wall is a target, and someone's firing arrows at the target, but you don't know where the target is. If the person fired an arrow and you saw a little arrowhead just appear through the wall there, would you know that that was where the target was? Not really, would you? You would have what's called a high level of uncertainty. Uncertainty is, yeah, like how certain you are about your result. Like how, if you've said that the answer is 1, could it be 1.5 or 0.5, or is it exactly right? So if there was just one arrow there, you wouldn't have a clue, would you? If they fired like 10 arrows and you ended up with a little clump here, wouldn't you be pretty certain that the target was somewhere right in the middle of that clump, because you've repeated it, right? And the more times the person repeated it, the more certain you would be that the target was somewhere around there. If there was something wrong with their bow, if their bow was like bent a bit to the left or whatever, would repeating it 1,000 times help with the accuracy of that result? No, it would not, would it? Because you could end up with like a really precise little clump around here. But if the bow was just bent the wrong way, that still wouldn't be a very, very accurate result. So the reason that it's good to repeat results is because it gets rid of random errors. So obviously, errors. So an arrow being like a little bit to the left or the right, that's a random error. A bow being bent the wrong way, that's not a random error, so repeating won't help. But hopefully that helps you to understand. I'm trying to cover things that will help you with general practicals, because every module we do, there's going to be some kind of practical, and repeating your experiment is always a good way of getting a result. What would you keep the same in this ripple tank activity to make sure that your results were valid? This is another good question. What would you keep the same? So imagine that you've got your ripple tank and you want to measure the wave speed, right? So you measure the wavelength, you measure the frequency loads of times to work out the speed. What do you need to keep the same every time you measure? It's quite a hard question, this. It always catches people out. What do you need to keep the same? A lot of people on Facebook yesterday were saying things like, the water. But what about the water? Like, water's just particles of H2O, isn't it? It doesn't really matter if you take out a tablespoon of water and you put a different tablespoon of water in. So you've got to be a bit more precise. Is there anything that if you changed it, it would actually like mess up your results? It would change your measurements. It's quite hard. Like, people were saying the light. And I was like, well, the light isn't anything to do, it's not going to change what you're measuring, is it? The waves aren't going to go like faster or slower because you break a light bulb, so you replace it again. Let's see what I've got. I put the depth of the water, the angle of the tank, which is kind of the same thing, isn't it, if it's on a slight slant. I put the frequency of the paddle. I think all those things are going to affect your actual result. Okay, right, let's move on. Do you remember we were talking about angle of incidence? Does that ring a bell? Angle of reflection, angle of refraction. You've got to talk about an activity where you get a glass block or some kind of different shaped block, you shine light through it, and then you see what happens. What does happen? Well, let's have a little look. It took me ages, this PowerPoint. I'm not entirely sure it's worth it, but I'm going to show you it because I did it. Here we go. So this is a practical to investigate the refraction of light using different shaped blocks. Here is the equipment that you need. The light box. You might not have seen one of these before. It's an electric light bulb in a box, but the box has got a little slit in it, so it makes this lovely, almost like laser style beam of light coming out the box. You need a protractor, you need a pencil, you need a ruler, you need some paper, and you need, I put Perspex blocks, kind of plastic or glass block, whatever you're testing. What are some dangers to look out for? What are some dangers? There's no water this time. Electricity is always dangerous, isn't it? This bulb will get very hot, and the black bit is made of metal. So that's one of the dangers of this activity, is be careful not to touch the light box because it will get very hot. Right, so you get your paper, you get your glass block on your bit of paper, you draw around it, you ready? So you can then get rid of the glass block, and well, there's a couple of things you do here. First of all, draw the normal in. That's what you need your protractor for, because the normal is obviously a dashed line at 90 degrees to the block. And then, yeah, some experiments say you just shine your light box at the glass block and then draw the angles that the rays make. You can, if you like, set yourself up so you can get a protractor and measure. So this is the normal, right? So we're looking at angles of incidence here. So if this is light going into the block, that's an angle of incidence of 10 degrees. Is that okay? 20 degrees, 30 degrees, 40 degrees, etc., etc. And then you'd write out your table of results. So you're all ready to go. You've got your different angles of incidence, 10, 20, 30, 40, 10, 20, 30, whatever. And you're ready to shine your light into the block and see what the angles of refraction are and write them down. A little note that this is why having a really sharp pencil is important as well, because if you've used a really thick line, that's a larger uncertainty, isn't it? Can you see that if that was really thick, you wouldn't be quite sure whether that angle was 9 or 10 or 11 degrees. So sharp pencils, please, chokes. That was like supposed to be folks and chums, I think. And then you can get your glass block back on, get your light box out, shine it in, and see what your angle of refraction is. So we all know, don't we? If you shine it dead on like that, if it's along the normal, then the angle of refraction is 0. And then I got a bit bored at this point, to be honest, but you know what I mean. You shine the light in at these different angles and you put the results in. A little note on how to measure, how to draw your rays. So if this is the setup, you've got your glass block, you've got your light box. How are you gonna, you can't like get a ruler in, can you? Because that's a glass block, so that's not gonna work. What you do is you just draw a little cross in 2 places on the beam going in, and draw a little cross on 2 places on the beam going out. And then you can take your glass block away, and you can take your light box away, and it looks weird, it looks like you've not got enough, but as long as you've got 2 crosses, you can just join those up. And then you know exactly where your beam of light was. And then you can join them up in the middle as well. Phew, which one's the angle of refraction? Come on. It's quite tricky, isn't it? It's been a long time. Which one of those is the angle of refraction? This one's the angle of incidence here. Which one's the angle of refraction? stare at it with your eyes. It's most least dramatic reveal ever. That bit there. And you'd measure it with a protractor. Okay. And then you've got your table of results, right, with your angle of incidence and your angle of refraction, and you just plot them all into a graph. I've given you a past paper question, very similar to this. And they might well give you the table of results and get you to draw the graph yourself and then get you to say some results from it. Or you could do something which is very, very similar to that. Basically, the whole thing's the same, but you're investigating the refractive index. Oh, do you remember what refractive index is? Refractive index is how much a material slows the light down. And this is called Snell's law, actually, but it's the equation for refractive index. So N, which is a refractive index, equals sine of I divided by sine of R. And I showed you this. So we've got a block, let's say it's a glass block, the incident ray going in, and then the light refracts. So this is the angle of incidence, this is the angle of refraction, and we said, imagine the angle of incidence was 50 degrees, and the angle of refraction was 31 degrees. To work out how much the glass slows light down, what its refractive index is, you would do the sine of 50 divided by the sine of 31, and you get the refractive index of glass. Is that coming back to you? So in that situation, if you want the refractive index of the block, what you would do is you would plot on your graph. You'd have to add some more bits to your table of results and work out all the signs of your angle of incidence and all the signs of your angles of refraction. And then you can plot a graph. Why is it a genius idea to plot a graph? Because, look, do you remember, I think this was our very first lesson when we did the gradients of a graph. This line here going across and that line there are the gradients. So if we do sine I, which is just that line there, divided by sine R, which is that line there, it gives you the gradient, which would give you N. You're either totally following me or you haven't got a clue because you haven't seen the lesson, in which case you can look it up yourself. Why is it important to keep the same during that experiment? Another hard one, actually. You're shining a light into a glass block and you're changing the angle of the light and you're measuring the refracted angle. What would you keep the same? What would you have to keep the same in order to make it a valid experiment or fair test, if you like? Again, some people on Facebook saying the angle, but no, because that's what you're changing, isn't it? You're deliberately changing the angle of incidence to see what happens to the angle of refraction. So it's not the angle. Again, people were saying the light, but it's not the light because it's not going to make any difference, is it? If it's well, actually, I wasn't sure about that. There is a way that the light could be the right answer. What is it about the light that you don't want to change? If you just break a bulb and you just replace it, that's fine. What I've said is, what would make a difference is the colour of the light. If you're using green light and then your green laser breaks, you can't just use a red laser because they've got different frequencies, yeah, so they're going to refract slightly differently. And the other thing is the material as well. Well done if you're saying the material of the block, so like glass or perspex, the different kind of plastic will refract differently, so you can't change the glass. I think that's all I can think of, actually. Okay, last one, very quickly then. You've got to know how to measure the speed of sound in air. This is a good one. How do you measure the speed of sound in air? So you've got a couple of wooden blocks. You can smack them together and you make a noise. How would you measure how fast that sound wave was travelling through the air? What do you think? I'm just going to make you decide. I've given you some things. You've got a long tape measure or a trundle wheel, a friend, 2 wooden blocks, pencil, paper, way to write down your results, and you've got a stopwatch. What are you going to do? How are you going to measure the speed of sound in air? That's really hard, that. Measuring the speed of sound in air. What are you going to do? Well, if you're looking for a speed, what do you need? If you're going to measure speed, you need 2 other values. I'll draw a little picture on the board to help you while you're thinking it through. Come on, quickly sketch some diagrams. Can you plan out an experiment using just those things? Have you got it? Any ideas? You'll definitely understand once I show you this amazing picture. Yeah? So what you do is, you go somewhere big, like a playing field. You get your friend to go right over the other side of the playing field, and then you measure 100 metres, maybe with a very long tape measure, maybe with a trundle wheel, one of those awesome little wheels that it clicks every time you've gone a metre. So about 100 metres, could be further if you like. Your friend is holding the two big wooden blocks. They're cracking them together to make a sound. So what you do is, when you see the blocks come together, you start your timer, and when you hear the sound, you stop the timer. So then you've got a distance, 100 metres, and you've got the time it took for the sound to travel from the wooden blocks all the way to your ears. So you just do distance equals speed divided by time. Yeah? And then you can work out the speed. I've missed a couple of things out on purpose. How are you going to improve on this? Oops, that's just me. So this is a really simple explanation. There's a couple of things you could throw into here. Can you think about health and safety? Give me at least one thing you could do to stay safe, and something else you're going to have to need to do to make sure that you get rid of random errors. Stand 100 metres apart. One person bangs the blocks together. The other person starts the timer when they see the blocks move together and stops it when they hear the noise. The distance and time are used to calculate the speed using speed equals distance divided by time. At least one health and safety measure, please. And what should you be doing to improve the accuracy of your measurements? Take you back to my epic drawing. So I'm always banging on about this because I've got tinnitus. I think this person should be wearing ear protection. If you're smacking wooden blocks together far enough away that someone can hear it 100 metres away, wear ear protection. Some people on Facebook also very sensibly saying, do not drop the blocks onto your head. Hold the blocks tightly. It's a good one. And repeat. Well done if you said, there's absolutely no way you would have a very accurate result if you only did it once. You would do what's called finding the mean, right? Finding the average. I've set you a question about this as well. So you'd maybe do the experiment 10 different times, and then you'd add all the results together and divide them by 10, and that would give you a nice average, which gets rid of those random errors that we were talking about, like with the target on the wall. Okay, whew, right. I think we've made it through all the wave practicals that you need to know about. Hopefully that will have helped you with some other practicals as well that we will look at in the future. So yeah, next week we need to do signals, and we need to do the Doppler effect as well. It's a really fun one. And then yeah, I think I'm just going to try and test you as much as possible because it feels like we've been doing waves for a long time. And we really should be revising as we go. Okay, I'm just going to go to my Facebook page and see if any of you are watching live and have left me any messages. Other than that, thank you so much for joining me. If you want to support me, please do. That would be great. That's the only way I make money, is by people sending me £5 a month. Yeah, if you go to my About section and you click sign up, it takes you to this website called Coffee, where you can send me £5 a month. And you will receive Theatre of Science magazine, a past issue, but you'll receive the latest issue when it comes out. Oh, here's this. And I'll send you some rainbow glasses, diffraction glasses. You now know them as. Oh, hello, Tiger and Bird. Whoa, Tiger has just completed a 6-week Young Rangers course with Frog Life. Oh, in foraging and reptile and amphibian identification. Tiger, I need you in my garden so that you can tell me how many species of newt I've got. I've got some newts, but I don't know which ones they are, because some of the common ones have like a little crest, right? And I got all excited and I thought it was a rare one, but I don't think that it is. If I find one sitting on a log, I'll take a photo and send it to you. Oh, great. Well, thank you for that. Foraging and reptile and amphibian identification. I'm assuming you weren't foraging for the reptiles, although that would also be fun. Okay, I better go, because we're doing a lesson on fishing as part of the Coral Reefs module at 11 o'clock on Facebook. I might see some of you then. Thanks for joining me. Bye.